In this lesson, we're going to go over proving properties of parallelograms. And the nice thing is that we have seen these properties in coordinate algebra, so they should be review for us. A couple of key concepts to start with. Remember that a parallelogram is a quadrilateral because it does have four sides. And something that we haven't previously looked at is the difference between a convex and a concave polygon. A convex polygon does not have an interior angle greater than 180. So if you look at my convex polygon, none of my angles are greater than 180. But with a concave, look at this right here, this angle is greater than 180. So that's one of the differences between the two. The other has to do with the diagonals. And remember that the diagonals connect two vertices, just ones that aren't right next to each other. That would be a side, but connects two vertices, and for a convex, all of them lie inside the polygon, while with a concave, that is not the case. Remember that a parallelogram is a special type of quadrilateral, and both sides of the opposite, both pairs of opposite sides are parallel. So remember that's what these arrows mean right here. Those two sides are parallel, and then these double arrows means that these two sides are parallel. Excuse me. This is our symbol for parallelogram. And if we are talking about a parallelogram, then there are 5 theorems that are associated with it. Once again, we did see these theorems back in coordinate algebra. The first one is that if it's a parallelogram, then the opposite sides are congruent, so we have tick marks noting that. And notice that the converse is also true. If the opposite sides of a quadrilateral are congruent, then it is a parallelogram. The second theorem is that opposite angles are congruent, so angle A and angle C are congruent, and angle D and angle B are congruent. Again, the converse would be true as well. So we've got opposite sides and opposite angles both congruent. Consecutive angles are supplementary. So any two angles that are right next to each other, remember that's what consecutive means. So not opposite or across from, but right next to. Those angles are supplementary. The diagonals of a parallelogram bisect each other. So remember, diagonals connect two vertices that are not right next to each other, the two non-consecutive vertices. So here are my two diagonals, BD and AC, and notice that they bisect each other. So this has been bisected, BD has been cut in half, and AC has been cut in half. And the fifth one is that the diagonal of a parallelogram forms two congruent triangles. So if I draw my diagonal, it divides it into two congruent triangles. And we'll look at proving this a little bit later. Our first of 3 examples is looking at this quadrilateral and determining whether or not it's a parallelogram. So I'm going to go ahead and plot my points. So there are my points, my coordinates, and there is my quadrilateral. So I'm going to determine if it is a parallelogram. So notice I'm going to use, I'm going to look at opposite sides to see if they're parallel and to see if they're congruent. If they're parallel, remember they'll have the same slope. And if they're congruent, then they'll have the same length or distance between the 2 points. So I'm going to look at slope first. The slope of AB, if I do rise over run, is 1, 2, 3, 4 over 1, 2, 3, 4, 5, 6, so 4 over 6. And then it should be the same as DC. DC is 1, 2, 3, 4 over 1, 2, 3, 4, 5, 6. Alright, let's check AD. and BC. AD is rise 1, 2, 3, 4, negative 4 over 1. And BC 1, 2, 3, 4, negative 4 over 1 as well. So because I have the same slope, that's going to show me that both of these pairs of opposite sides are parallel. Alright, so I have parallel sides. That's what this shows me. Okay. Alright, remember that's my symbol for parallel. Sorry, it's a little, there we go, it's a little bit better. And now I'm going to look at the lengths of the sides. So remember, you can use the Pythagorean theorem or you can use the distance formula. I'm going to use the Pythagorean theorem. But this, if I do that, I'm going to connect these two. So this side length is 1, 2, 3, 4. And this is 1, 2, 3, 4, 5, 6. So if I look at that using the Pythagorean theorem, I've got 16 plus 36. So I've got 52. So that means this would be the square root of 52. I know this is the same side length because, remember, if you recall, it's the same slope. So again, we've got the square root of 52. Opposite side, I've got 4 and 1. So I've got 17. So the square root of 17 for both of these. So again, I've shown that opposite sides are parallel as well as congruent. So this would be a parallelogram. Here's this same parallelogram, and I'm going to prove that the diagonals of a parallelogram bisect each other. So what I need to look at is I need to find, one of the easiest things to do would be to find the midpoint, because remember, if it is bisected, then it would be divided in half, which would show me where the midpoint is. So I'm going to look at the midpoint of AC and the midpoint of BD. And if you recall, my formula for the midpoint is just taking the average of the x's and the average of the y's. So I've got negative 4, 4, negative 3, 0, 2, 8, and 3, 4. And I'm going to plug those in. Alright, so if I want to find the midpoint of BD, I'm going to use these 2 points. I'm going to add my x's together, 2 and negative 3. And then I'm going to divide by 2. And then find my y's, 3 and 0. So I end up with negative 1/2 and 3/2. Alright, so let's check that. Negative 1/2 and 1, 2, 3. Oh, excuse me. Negative 1/2 and 3/2 would be 1.5. Well, that doesn't seem right. Guess would help if I made this an 8 like it's supposed to be. Let's try that. Which would be 4. And that looks a whole lot better. Sorry about that. So negative 1/2 and 4 puts me right here. Let's try that with our other segment, AC, our other diagonal. I'm going to add my x's together. and then add my y's together. So I end up with -1/2 and 4. Again, same spot. So I was able to prove the diagonals bisect each other by looking how the midpoint is exactly the same for both. Alright, our last example is going to use this same parallelogram, and I'm actually going to write a proof about how this diagonal separates it into two congruent triangles. Alright, so let's go ahead and write a proof. Remember, this is the same example that we've been working with, so we're actually going to, not cheat, but we're going to use our information that we've already shown through numbers 1 and 2. Alright, so here are my statements and my reasons. The first statement that I'm going to make, we don't have any givens, but I'm going to talk about, in the first example we showed that the opposite sides were congruent. So I'm going to state that. I've got AB is congruent to DC, and I'm going to say AB is congruent to BC. I'm going to say opposite sides of a parallelogram are congruent, and I'm going to also put proven in number 1. Alright, the second thing I can say is I can actually say that BD is congruent to itself. Does anybody remember what that's called when segment or angle is congruent to itself? If you recall, that's called the reflexive property. Sorry about that. Alright, and now we've got actually all 3 sides, so I can prove that those 2 triangles are congruent. So triangle ABD is congruent to triangle BCD by side, side, side. Steps 1 and 2 really have everything we need in there. So hopefully, like I said, this is a review of what we did in coordinate algebra. And in the next lesson, we're going to go on to looking at the special types of quadrilaterals, such as squares, rectangles, rhombi, things like that.